Okay, let's go over your accumulation functions homework. So for our first problem that we have, notice they've given us a chart that we need to fill in, and we do need to show our work on this. So our first problem that we have, again, you need to recognize how our function is defined, and that function is up here. And so for our first problem, we are substituting in a -1. So we need to look at f at -1, which is going to be the integral from 0 to -1 of f at t dt. And so we would really need to invert our endpoints here. So we'll do that here in a minute. So we're going to go from -1 to 0. And so looking at that region, here's -1. Here is 0, so we do have that trapezoid, and so looking at this we can figure out our sides and our shape. So up here the height we have is 6 and the other height that we have is 4. So our formula is going to be 1/2 the height, which is 1, times the sum of the bases, so 6 plus 4 is 10. So notice that gives me 5, but I do need to invert those endpoints, so that's really going to make that a -5. Okay, so I now know that part is going to be -5. All right, and so now let's move on to our next. We're going to substitute in 0, and we will see that f at 0 is just going to be the integral from 0 to 0 of f at t dt, and that is just going to be 0. And then f at 1, that's going to be the integral from 0 to 1 of f at t dt. And so from 0 to 1, we have our bounded region. Here from 0 all the way out here to 1, there's our region again, and it looks like we have another trapezoid there. And so we're going to do 1/2 our base times the sum of our 1/2 the height times the sum of the bases. So this one is going to be a 4. This height is 2, and so here this height is going to be 1, and so that's going to be 1/2 the height times the sum of the bases, which is going to be 6. So it looks like that's going to be a 3 for us. And continuing on this same process, we are going to substitute in 2, and we just repeat the process here. So f at 2, that's going to be the integral from 0 to 2 of f at t dt. And so from 0 to 2, notice we're going to have a large triangle here, or we can make a small triangle and add to what we already had if you wanted to look here to here. Either way, so if we look at the big triangle there, we've got 1/2 the height, which is 4, times the base, which is 2. And so f at 2 should be 4. And then continuing on again, f at 3. So now we're integrating from 0 to 3 of f at t dt. So that's going to give us from 0 to 3. Notice we still have this region here, but now we have this small part that's going to become negative. And so for there, I know from 0 all the way over to 2, we found that region is going to be 4. And then I've got to subtract from that this smaller region here. So we're going to do 1/2 the base, and that base looks like it's going to be a 1, times the height, which is 2. And so that's going to give me 4 minus 1, which is 3. And continuing on, we need to find the integral, or f at 4, which is going to be the integral from 0 to 4 of f at t dt. Well, I already know from 0 to 3, I know that's going to be 3 already minus, and if we go all the way out here to 4, well, we can do another trapezoid, or we can make a huge triangle here. Either one is fine. Most people would probably rather make a triangle. So I'm going to erase that 3 there, 3 minus, because we'd rather probably do the triangle. So that region there, we've got 1/2. And then the base is going to be 2. And the height is 4. So that's going to give me a 4 that's bounded under. But now we also saw from 0 to 2, it was positive 4, so that's going to give me a 0. So we really found a 0 for the function there. And then all the way out to 5, again, we can make a large triangle there. And again, we are finding f at 5. So that's the integral from 0 to 5 of f at t dt. And so we can make this large triangle here. And if we do so, then we have our 1/2, our base times our height. So I'm just going to write this up here. We got 1/2. Our base is going to be from 2 to 5, so that's 3, times our height, which is all the way down here at 6. And so it looks like we're going to end up with 1/2 of 18, or 9. And so really that's a -9 in that region because we are bounded below. So I have -9 plus, and we know from 0 to 2, we found that area to be 4. So that's going to give us -5. All right, so we have all of our values. We have all the individual information. Now let's go over and look at part A. And really, when you're answering these, you want to know over what interval is f positive. So whenever you're talking about your function f, then you have to be careful and look and see, well, where are we above here? Because we're not talking about big F. We're talking about little f, which is our function that we're given over here. This is our f at x. It is right there. So where is f positive? Well, f is positive from -infinity all the way up until +2, because that's the actual graph we're looking at. And f is negative, well, that's going to be from +2 to infinity. Now the question C is changing. We want to know, where is f increasing? Well, we can look at this a couple of different ways. If you want to know about f, since f is defined the way it is, we know that f prime is really the graph that we have here, is really that f of x. So if f is increasing, then I'm looking to see where my function is positive. Well, this function is going to be positive or increasing on the interval from -infinity to 2. Notice you got the same answers for here to here, and that's because where f is positive, that means that my function is increasing. So here, where are we decreasing? Well, that should mirror the value that we got in B. That's going to be from 2 to infinity. And the reason why, again, if my original function is decreasing, then its derivative is negative. And it turns out this derivative that I'm talking about is our actual graph. All right, now as far as part E, plotting the points and seeing, no, we're not going to look at that. Okay, for our next homework problem, we are going to be setting up different types of integrals, and we're going to be applying what it means to actually integrate from a point to a point. And so here, notice that we're given f at 1 is 13. So that's a value we know for sure. And we're asked for, really, we've got to find this value at -3. Now we know f of x is a differentiable function on a closed interval, so all this stuff's going to work that we've been going through. So don't let the wording bother you. All right, so setting up using what we know, we need to find -3, and I know +1, so we're going to integrate from -3 to +1, of f at t, or let's see, this one's labeled x, so f at x dx is equal to f at 1, it's top endpoint minus the bottom endpoint. All right, so we know f at 1 is 13, so I will be subbing in that value, but I also need to go back over here and find this bounded region. So from -3 all the way over to a +1. So I have this region here. And so really we can divide this up. I think most folks would probably want to divide this into maybe a rectangle and a triangle. And so if I find that region there, I'm going to go ahead and just highlight this. And if we do 1/2 our base times our height, that's going to give us 10 inside there. And then if we go through and, well, 10 times 1/2, sorry. I gotta take half of that. So reckon that it's going to be 5, 1/2 base times height. And then we've got to also find this other region. And so when we find that, that's going to be length times width. And so if we find that area, that's going to end up being, so here if we do 2 times 5, that's going to generate a 10 for us. And so we now have enough information that we can finish the problem. So we're going to have this area here. It's going to be 5 plus 10, so we're going to have 15 equals our f at 1 value minus f at -3. And so we're going to have 2 equals negative f at -3. So -2 is going to be f at -3. So we now have that ordered pair here, -3, -2. All right, so now we're going to repeat our process, and we've got to find 0 next. So using what we know, we are going to integrate, and we have 0 and 1, so we're going to integrate from 0 to 1 of f of x dx, and we know that's going to be equal to f at 1 minus f at 0. And so we need to integrate from 0 to 1. So that's really half of this rectangle that we're seeing from 0 to 1. So we know that's going to be 5 is equal to f at 1, which is 13, minus f at 0. And so when we solve for that, we should end up with a +8. We know f at 1 is 13, so now we're going to find 2. So again, we are integrating from, we're given it 1 and we need to go to 2. So from 1 to 2 of f of x dx. And again, I know that's going to be equal to f at 2 minus f at 1. So integrating from 1 to 2. So we need to now find this other portion inside here from 1 to 2. So we need to find this small bit here. And so we're going to do 1/2 our base times our height. So that looks like that's going to generate for us 2.5 in that area there. So down here I know I have 2.5 equals f at 2 is what we're looking for minus 13. And so when we add that 13 over, it looks like we're going to get 15.5. All right, so continuing on, we need to now integrate since we're finding 3. Oops, I need to change my pen. So we're going to be integrating from 1 to 3 now of f of x dx. And again, I know that's going to be f at 3 minus f at 1. And so again, finding that bounded area from 1 to 3. So we have 1, we know what 2 is, and now we've got to find 3, so that small region down there. So 1/2 base times height. So it looks like that small region is going to be 1.5. So here I know that area is 1.5. And again, repeating this process, and we do need to put those together. So 1 to 3, so I know 1, well, that was 2.5 minus 1.5, so I know that's going to be a 1 equals f at 3, and so that's what we're looking for, minus f at 1, and f at 1 is 13. So it looks like we're going to end up with 14 for f at 3. And we continue on the same process. You should get 11 for 4, and for 5 you should get 8. All right, so now let's go over and answer some of these questions again, and they're very similar to what we just looked at. Notice the first one, this is asking us on what intervals is f positive, and so notice that's just talking about our graph, and so that's going to be from -3 all the way over to 2. There's the interval where I'm positive, and so that would imply that's where, oops, I made that way too long. That's going to be where f is increasing, because lowercase f is the derivative of uppercase. So here, again, that should be from -3 to 2. And then part B, on what intervals is f negative? So that's talking about the graph. So over what interval is the graph below the x-axis? And that's going to be from 2 to 5. So by that same reasoning as earlier, that's going to imply where f is decreasing, which is from 2 to 5. And again, I don't care if, oh wait, no, that's not the graphing. Oh no, let's go back. 4 from -3 to 5, so I'm looking at these intervals here and here from -3 to 5. Oh, I'm losing my mind. From -3 to 5, find the value at which x has, which f of x has an absolute minimum. So that's going to be the smallest value. So if we're looking at the absolute minimum, then there's a few things we have to go back and try. And this is a good review for us. Absolute minimum means that we have to try our endpoints. So I need values for, and keep in mind this is the absolute minimum of f at x. So I need to test -3. I need to also test 5, and again that's because it's an absolute minimum. And then I also need any critical points. I need to know where those critical points are. So that critical point, if I'm talking about a minimum, then that critical point, that means that f, capital F prime, if it's a minimum, went from less than 0 to greater than 0. So what does that imply about f of x, lowercase f? Well, if here f prime, if the derivative is negative, well, that's also talking about where f is negative. So I need to know where f went from negative to a positive. So we're also going to have to look at what's going on around f at 2. So here, the only other place that we have a possibility would be at 2, but notice what's happening here. I need f to go from negative to a positive, but that doesn't happen at 2. 2 is going to be a relative max, so, or possibly an absolute max, but again, we need to toss that out because I'm talking about an absolute minimum. So we're back to the old integration, and I'm going to mark out part F, and we need to integrate, and which we might already have. Do we have a value for -3? So let's go back and look. We need to find f at -3, which we can integrate here. And what do we know? What values do we already know? We know 1. And what else do we know? But I'd rather, even though we do know that f at 1, I'd rather go back and use our chart if we could. So I need to find the value of f at -3. So let's see, we can go from -3 up to 0 of f at x dx. And I know that from 0 to -3, or -3 to 0, I know that is 5. So let's go ahead and fill in the rest of it, though. We know that's going to be equal to f at 0 minus f at -3. And again, here we're going to find this integral. So from -3 over to 0, we have 5 plus 5 more, because this portion here is also 5. So that's going to give us 10. And so we know f at 0 is 8. So we're going to have 10 equals 8 minus f at -3. And so if we subtract, it looks like we're going to get a positive 2 for f at -3. So there's positive 2. And so now we need to talk about 5. And do we have a value for f at 5? F at 5 we've already found. It's right here. It is 8. So the absolute minimum is right here. Absolute minimum value for the function, or it just says find the x value. So x is -3. That's going to be where our absolute minimum occurs. Okay, for our next question, we are given a function, but this time we have to be really careful about how it's defined. If you notice here, our endpoint does not start at 0. It is starting at 2. So that does change a little bit. The graph of f on the interval from -2 to 6 consists of 2 line segments in a quarter circle. And so the first thing they're asking us to find is f at 0. So if we go through to find f at 0, we are going to be integrating from 2 to 0. And again, that's because that bottom is 2. Of f at t dt. And right away we see we need to flip our endpoint, so that's going to be from 0 to 2, f at t dt. And now we just need to go over here and find that bounded region. So from 0 to 2, then that looks like we're going to have a nice triangle here. And so that region, once we look at 1/2 base times height, it looks like we're going to have an area of 2. And so we still had to invert our endpoints. So f at 0 is going to be -2. Okay, so for our next part, we've got to go through and find f at 4. So f at 4 is going to be equal to the integral from 2 to 4 of f at t dt. And again, I'm starting at 2 simply because that's what we're given up here. And so we need to go over and find that bounded region. And so this is going to be a quarter of the circle. And so our formula is pi r squared, but then I need to divide that by 4. And so that's going to leave us just with pi. And so this bounded region is going to be pi. All right, so for part B, determine the interval where f of x is increasing and justify your answer. So I do know that f of x, here if I do the derivative, that's equal to just the graph that I'm given, which is going to be f of x. I know that to be true, and I also know that where f prime of x is greater than 0 or positive, which in turn talks about f of x being greater than 0, then f of x is increasing. So there's my justification. I'm just stating the rule at which we're going to use. And now the interval over which this occurs, where's f of x positive? Well, that's going to be from 0 all the way over to 4. So we know from 0 to 4. And where else would this function be positive? And that's going to be from 4 to 6. All right, so now let's look at C. C says to find the critical numbers of f of x, so I'm going to stop there. If we talk about critical numbers, then that means I need to find where f prime at x equals 0. So again, that's going to be finding a critical number for f of x. But again, we know that f prime at x is equal to f of x. So really, if I knew where my function graphically is 0, then I've got all of my critical points. So if we go looking at all of these, then let's see, that's going to happen at x equals 0. And we also have when x equals 4. Okay, so now we have our critical points. We have found those. And now let's talk about, determine if each corresponds to a relative minimum. So I need to classify these whether or not it's a relative minimum. So I know a relative minimum exists where f prime of x changes from negative to positive. So let's just write that out. We're going to say a relative min occurs when f prime of x, which is equal to f of x, changes from negative to positive. And so let's look at our graph and see, well, where does that happen? Well, from a negative to a positive, that's going to occur right here at 0. So that tells me the relative min is going to be x equals 0. Is a relative min. Now, what about 4? Well, notice that even though we have f prime is 0 at 4, there's no sign change here. So we can go ahead and say at x equals 4, or x equals 4 is neither a relative min or max. So you can state that. Nothing really says you have to. I'm going to go ahead and just write it in though, just in case you were asked. So here we're going to say at x equals 4, there is no sign change. In f prime at x. So x equals 4 is neither. And that's pretty straightforward. That's all they need from y'all. So moving on to part D, you're asked to find the absolute extrema. And so that's talking about your absolute min or max, which means the only difference in this and your relative is the absolute, you have to use your endpoints. So really, let's discuss all of the x values that we need to determine our absolute min and max. Well, you definitely need to have your endpoints, and if we go all the way back to the beginning, we were told that we had a closed interval from -2 to 6. So there's my endpoints. And then you also need your critical numbers. So let's make a note here. That means endpoints if you're looking for your absolute, and you also need critical points. That's so important for us to have those. And we identified our critical points to be 0 and 4 from the previous problem. Now we also saw that at 0, what did we find for f at 0? Did we do that one yet? I think we did. And f at 0, I think we ended up with -2. If not, let's go ahead and work through it, but we'll go through these in order then. So the first one we need is to integrate, and keep in mind how f of x is defined. Let me go ahead and just rewrite that. So f of x is defined to be the integral from 2 to x of f at x, or f at t dt. So for our first one, we need to find f at -2. So that means I'm going to integrate, and I'm going to go ahead and flip my endpoints because I know that -2 needs to go down here, of f at t dt. So I need to integrate from -2 to +2. And so if we look at -2 to +2, if you find that bounded area, you're actually going to have -2 to 2. That's going to give you 0 there if you calculate that bounded area. So I know that first one is 0. Now I need to find f at 6, which again I'm going to be integrating from 2 to 6 of f at t dt. So let's go find that bounded region, and that's going to be from 2 all the way to 6. So it looks like that's going to be 4 plus pi. Okay, so 4 plus pi, and that looks like that's probably going to be the biggest. But let's just make sure. If we find 0, so let's see, f at 0, I need to go through and know that here we're integrating, we're going to have to flip over. So that's going to be here from 0 to +2 of f at t dt. And so let's see, what's that going to be? From 0 to 2. So that's +2, but then the negative there is going to throw that at -2. And notice at 4. So here at 4, let's find that region, f at 4. So again, from 2 to 4, f at t dt. And that value from 2 to 4 was pi. All right, so here we're looking for our relative extrema. So that's telling me here that I need to find the biggest and smallest value. So let's see, our biggest value was right here. So at x equals 6, we have a relative maximum, and at x equals 0, we have a relative min. All right, so now let's look at part E. And part E talks about that point of inflection. So that means our second derivative, and we've not really talked about that in a while. So let's go through our chain. We know that f of x is the integral from 2 to x of f at t dt. We know that. And then I know f prime at x is equal to just f at x. And then f double prime, because I want to know a point of inflection for f of x. So f double prime of x, that's going to talk about f prime at x. So a point of inflection means that's where my second derivative equals 0 and changes signs. So that's what we're looking for here, is where you equal 0 and you have a sign change. So in this part, f double prime is 0. That really translates back to f prime at x equal to 0. So where am I going to have these zeros happen? Or it can also be where it doesn't exist. But let's look and see, where do I have a sign change? And that's going to be here. Well, we can have a sign change where we're increasing to decreasing, or something along that nature. So let's see. If we have a sign change for this, and we need to make sure we're going, let's see, this is our graph of our derivative. Oop, we need lowercase. So this is really the graph of the derivative. And so f prime, that's really talking about the second derivative of the original. So where am I going to have a sign change? Well, where do I stop changing from increasing to decreasing? That's going to happen right here. So that tells me I know at x equals 2, there's a point of inflection because I changed from increasing to decreasing. And then there should also be another one over here at 4 because I changed from decreasing to increasing. So let's write that up. So I know that I have a point of inflection at x equals, and we set it 2, and x equals 4. Now our justification, why in the world do I know we have that to happen? Because I know that f prime changes from increasing to decreasing. To decreasing, or vice versa. So either way, so you have that change going on. Okay, so now for the next part, determine the intervals where the graph of f of x is concave down. So I know f of x is concave down when f double prime of x is negative. And then I know f double prime of x is actually equal to f prime at x. So, well, that's just going to talk about where is f double prime of x less than 0. Well, f prime of x, goodness, is less than 0 when f of x, oh my goodness, is decreasing. That is some crazy stuff right there. So basically, I need to pick out where this graph is decreasing. And so where would I be decreasing? Well, that looks like we are decreasing from 2 to 4. F of x is decreasing on, oops, my pen's about dead, from 2 to 4. All right. For our next homework problem, it is very similar to the other problems. Notice how g of x is defined, and notice that f of x is really the graph that we're given. So over to the side, again, a quick run through. We know that g of x is defined as an integral of another function, and we would also then know that g prime at x is equal to f at x, and g double prime at x is equal to f prime at x. All right, so keep in mind that our graph, again, that is going to be f of x. This is what we're given. So notice in part A, it asks us over what intervals is g of x increasing. So in our justification, it's really you're just writing what you used. So if g of x is increasing, let's think through this, then that tells me that g prime at x is positive. And so g prime at x is the same thing as f of x, or my graph. So where is my graph positive? Well, my graph is positive or above the x-axis from 0 to 4, and where else would be from 8 to 12. Now there's where g of x is increasing. Now we need to justify my answer, and the justification is g of x is increasing because this is where f at x is positive. All right. So let's look at part B, determine the intervals in which g of x is decreasing and justify your answer. So g of x here is going to be decreasing where f of x is negative. And so that's going to be from 4, or the interval from 4 to 8. We're going to say g of x is decreasing because f at x is negative. All right, so moving on to part C, this asks us to find the x-coordinate where g of x has a local min or max. So this local min or max is the same thing as a relative min or max. That's the same thing. And let's talk about justify your answer. And so to get a relative min or max, the very first thing you would have to know is a critical point. And keep in mind that a critical point, and this is kind of over the side thinking, that a critical point is going to be where g prime at x equals 0. That's what I need to be thinking, is we have to find those critical points. So g prime is equal to 0. If we translate that to this problem, we're really looking for where f of x equals 0. So f of x is going to be 0 when x equals 4 or x equals 8. And so that's our critical points. Now we do have to label those local min or max. So let's go look and see which one's going to be which. Keep in mind, if we talk about a relative min, that means that my function went from decreasing to increasing and max increasing to decreasing. So over up here on the graph, notice that 4, x equals 4, f of x changes from a positive to a negative. No, yes, positive to negative. So that would imply that we have a relative, and positive to negative, that's going to be a relative max. And then over on the other side for x equals 8, f of x changes. I'm going to run out of room here. F of x changes from negative to positive. So that tells me we have a relative min. All right, now let's go look at part D. And in part D, we are asked that to find the x-coordinates where we have a point of inflection. So that point of inflection, that's going to be where we kind of have those turns, but now it's a point of inflection on g of x. So thinking about this a moment, and I'm going to move up here, a point of inflection, well, that's where g double prime of x is going to equal 0. And so I know g double prime of x in this particular problem translates to being f prime at x is going to be 0. And so that's going to be talking about the slopes of our graph of our derivative. So we're going to have that being 0 over here, and we're just going to call this 2, as f prime is going to be 0. Right here, f prime is 0. And right there, f prime is also 0. So these things are going to happen when x equals 2, when x equals 6, and when x equals 10. There's your points of inflection. All right, so, and our justification is going to be, let's go ahead and write that up. So x equals 2, x equals 6, x equals 10 is the point of inflection because that is where f prime of x equals 0. And we can say and has a sign change. All right, so now let's look at where g of x is concave up or down. And this is where it gets a little tricky. G of x concave up or down. Well, we know that if g double prime of x is positive, then we are concave up. Well, that translates in this problem to being f prime at x is positive, which then in turn, if f prime is positive, that means that's where f is increasing. That's going to give me concave up. So if you're given this situation and you're asked for concave up or concave down, you're basically looking to see where is this function increasing or decreasing. So we are increasing from 0 to 2. And we're also increasing from 6 all the way up to 10. That's going to be where you're concave up. And then concave down, well, that's going to be where f prime at x is going to be less than 0, because then f is decreasing. And so that's going to be from 2 to 6. And it's also from 10 to 12.